Our group's physics topic that is explained in this video is called Laser-Induced Breakdown Spectroscopy. Laser-Induced Breakdown Spectroscopy, or LIBS for short, is a chemical analysis technique that uses short laser pulses directed toward a small sample of material. In a process called laser ablation, a laser pulse causes the electrons in the atoms of the material to become excited and rise to higher energy levels, creating a small pool of plasma on the top of the sample. When the plasma cools, the electrons move back down to a lower energy level, emitting The emitted light from the plasma is collected and coupled with a spectrograph detector module, which creates displays of the detector's spectral wavelengths. Each element on the periodic table is associated with unique spectral displays, which allows the chemical composition of any sample to be determined. This function of LIBS is used in many fields, including medicine, which we will elaborate on later on in this video.
Laser-induced breakdown spectroscopy heavily involves the use of a laser, which is actually an acronym for light amplification by stimulated emission of radiation. In order to understand how a laser works, we can go back to 1913 and Niels Bohr's model of the atom. It was the first of its kind to incorporate quantum theory, and that accounted for the discrete wavelengths that they found in emission spectra. The Bohr model describes electrons in set values in a series of circular orbits. So the energy lost by an electron and the abrupt transition between energy levels is the same as the energy of a quantum of light emitted. In 1917, Einstein came up with the concept of stimulated emission, which is fundamental for the function of a laser. The three main properties of a laser include line width, coherence, and power. A narrow line width indicates a nearly monochromatic beam, which is tied to a single frequency. Coherence allows for the focus of photons to form a beam, and power just refers to the high-intensity light produced by a laser. Stimulated absorption occurs first in the cavity of a laser. Electrons naturally exist in their ground state. However, electricity from a high voltage power source can excite the electrons when it's applied to atoms of a special glass, gas, or crystal in the cavity of a laser. Excited electrons are pushed to higher energy levels. Then, stimulated or spontaneous emission can occur. The farther the fall of the atom, the higher the energy of the emitted photon will be. Once emission occurs, the emitted energy perpendicular to a partial mirror in the laser cavity is reflected and constructive interference occurs, allowing for the creation of a standing wave and a resulting beam. In order to have an effective laser, a huge number of photons must be working together. The laser most commonly used in laser-induced breakdown spectroscopy generates energy in the near-infrared region of the electromagnetic spectrum. Now let's talk about how a laser works in LIBS.
Specifically, during laser ablation, the laser pulse is absorbed by a small area of the material, breaking chemical bonds in that area. Bonds between specific elements have specific bond energies that must be matched by the energy delivered by the laser. A high-intensity laser is able to make the atoms in the particle change to a gaseous state. When the atoms of the gas are ionized after the laser pulse, it forms plasma, which is a medium with approximately equal number of positively and negatively charged particles. Energy is then emitted from the plume of plasma in the form of light, satisfying conservation of energy. The light is collected from a lens or optic cable on a spectrograph, which measures wavelength and intensity at specific wavelengths. Using computer software, graphs can be made plotting wavelengths and intensity, creating spectral lines. Software then compares the created spectral lines to known wavelengths to identify the elements present, then analyzes the intensity of the spectral lines to determine the concentration of those elements. With laser ablation, a person can focus on very small, specific spots because minimal excess heat is transferred to surrounding areas. LIBS is also beneficial because laser ablation requires little to no sample preparation.
There are numerous factors that contribute to the success and efficiency of such laser ablation techniques. The first one is wavelength. A high energy deposition with a low volume of matter is ideal, which is largely due to the type of wave that's delivered to the sample. Next is pulse duration. Shorter laser pulses allow for maximum peak power. Then we look at pulse repetition rate, which must be high enough for the heat to be maintained, usually thousands of pulses in just 1 second. This reduces the energy lost in between pulses with little to no cooling of the plasma. The last factor is beam quality. The size of the beam must be controlled, along with its brightness and focusability, in order to properly deliver a high amount of energy to a very small region of material, often measured in micrometers.
Laser-induced breakdown spectroscopy, or LIBS, has several applications throughout society, including food analysis, governmental research, and medical detection. Especially in the medical field, LIBS has been predominantly used to detect and diagnose malignant cancerous tissue. Initially, this was done by using the LIBS system to obtain a spectra that could be used to analyze the concentrations of the certain elements in the tissue, such as calcium, sodium, magnesium, and copper, that enabled the researcher to determine if the tissue is cancerous. This can be done because in malignant cells, the concentration of calcium, sodium, and magnesium is seen to be significantly higher, whereas the concentration of copper is lower when compared to normal, healthy cells. Not only are these tissues detected through the analysis of elemental concentrations, but LIBS has also been used to detect certain biomarkers for cancerous tissue through the use of an elemental tag. For example, in a study, this was done through a LIBS-based detection of silicon in the emission spectrum that indicated the presence of the biomarker for ovarian cancer. The use of LIBS in medical research was seen in a 2010 study where the system was used to identify colorectal and breast cancer. This was done by measuring if there was a significant increase in the abundance of calcium and magnesium concentrations that is characteristic of malignant cells. In the study, it was seen that there was an increase in both calcium and magnesium as observed in the atomic absorption spectrometry, which displayed the existence of a cancerous tissue. This can be seen in the graphs where the calcium and magnesium concentrations were far significantly higher in malignant cells, the red bars, than in normal, healthy cells, the green bars, for both colorectal and breast cancer.